Hello, welcome to the third unit, matrix decomposition and pseudo-inverse of a matrix. In this video, we are going to see the spectral decomposition of a symmetric matrix. The spectral decomposition of a symmetric matrix. We know what is meant by a symmetric matrix. A matrix is said to be symmetric matrix whenever if you interchange rows as columns or columns as rows, and if you are getting the original matrix, we say that it is a symmetric matrix. Now we are going to see the spectral decomposition of a symmetric matrix. So what is this spectral decomposition? So it is also known as the eigen decomposition, spectral decomposition or eigen decomposition. It is nothing but it is the factorization of a matrix into canonical form. Factorization of a matrix into canonical form, where the matrix is represented in terms of its eigenvalues and eigenvectors. In terms of eigenvalues and eigenvectors. So only diagonalizable matrices can be factorized in this way. So spectral decomposition or eigen decomposition is nothing but it is just a factorization of the matrix into a canonical form, where the matrix is represented in terms of its eigenvalues and eigenvectors. Let us see first what is the statement of the spectral decomposition theorem. So the statement is like this. So let A be n by n symmetric matrix, any square symmetric matrix. So given orthonormal eigenvectors x1, x2 and so on xn corresponding to the eigenvalues lambda 1, lambda 2 and lambda n, then A can be written as A equals to PD P inverse. We have seen this one. So what is here? A is the symmetric matrix. What we have to do? First calculate the eigenvalues for that matrix. Then you will get lambda 1, lambda 2 and so on, lambda n are the eigenvalues. So corresponding to these eigenvalues, next we have to calculate the eigenvectors x1, x2 and so on xn. Once you got the eigenvectors, next you have to check it whether they are orthogonal or not. If they are orthogonal, then make them as orthonormal. That means you have to divide each vector with its norm. Then you will get this set of orthonormal vectors x1 bar, x2 bar and so on xn bar. Then this A can be written as, according to the diagonalization, A can be written as PD P inverse. But what is this P inverse? P is inverse is nothing but P transpose, because P is what? It is an orthogonal matrix. Therefore, if it is orthogonal matrix, its inverse is nothing but its transpose. Therefore, A can be written as PD P transpose. So here D is what? The diagonal matrix. So with the diagonal entries, lambda 1, lambda 2 and so on lambda n. Now this equation A equals to PD P transpose, it becomes like this. P is this one. D is the diagonal matrix whose principal diagonal entries are nothing but the eigenvalues, and P transpose, you have to take transpose of this. So if you multiply this, in the first phase you will get x1 bar into lambda 1, x2 bar into lambda 2 and so on xn bar into lambda n. Then this vector, this column vector is as it is. Next, if you multiply this row vector with this column vector, you are going to get this one. So this expression, whatever you are getting, A equals to this one, this is called the spectral decomposition of A. So it is known as the spectral decomposition of A. So clearly, if you observe here, we written A, this A. What is this A? The given symmetric matrix. We are writing it into spectral decomposition form, where this form is consisting of the eigenvectors and the corresponding eigenvalues. So we are writing this in this form. So this type of expression is known as the spectral decomposition. Now we'll see all this with the example, with the help of one example. So the example is this one. Find the spectral decomposition of the matrix A. So a matrix is given, 3 by 3 matrix. If you observe clearly, it is a symmetric matrix. So if you make these rows as columns, you will get the same matrix, so which is a symmetric matrix. So what is the procedure to write the spectral decomposition? First, you have to get the eigenvalues for this matrix, then the corresponding eigenvectors, then check it whether the eigenvectors are orthogonal or not. If they are orthogonal, make it as orthonormal. That is, we have to divide every vector with its norm. That is the criteria. Okay, so first we are calculating the eigenvalues for this symmetric matrix. So the procedure we know already. So first you have to write the characteristic equation. So the characteristic equation is a minus lambda I equals to 0. So from this what you will get, 3 minus lambda minus 1, 1, minus 1, 5 minus lambda minus 1, 1, minus 1, 3 minus lambda equals to 0. Now solve this equation. So you will get a cubic equation here. So we factorized that cubic equation here and we got the eigenvalues as 2, 3, 6. So 2, 3, 6 are the eigenvalues of the matrix A. Next, consider the system. So a minus lambda I into x equals to 0. So this is the system. So we are naming this one as 1. So we will use this system to get the eigenvectors. So first I am getting the eigenvector corresponding to the eigenvalue lambda equals to 2. So what I have to do? I have to put lambda equals to 2 in this system 1. So if I put in this system 1, 3 minus 2 is 1, minus 1 as it is, minus 1, 5 minus 2 is 3, minus 1, 1 minus 1, 3 minus 2 is 1. So this is the matrix we got. Now I have to make this matrix into echelon form, or we can say it is upper triangular matrix. I have to make it. That means the entries below the principal diagonal, I want to make it as 0. So for that purpose, what I am doing, I am adding the second row with this first row. So minus 1 plus 1 becomes 0. 3 minus 1 is 2 and minus 1 plus 1 is 0. Similarly, if I add row 3, R3, sorry, if I am subtracting R1 from R3, so R3 minus R1 is 1 minus 1, 0, minus 1 minus of minus 1 plus 1, 0, 0. So now this is in the upper triangular matrix form. So from this, by back substitution, if I go, so 2y is 0, that implies y is 0. Next, x minus y plus z equals to 0. Already y is 0, therefore we get x plus z is 0. This implies x is minus z. So now what I will do is I will choose this z is some constant. So I am selecting choose z equals to k here. So if I select z equals to k, my x is minus k and y is already we got it is 0. Therefore, x, y, z equals to minus k, 0, k. So k I taken outside, so which is minus 1, 0, 1. So where k is a scalar which is not equals to 0. So if I choose k is 1, so I am going to get the first eigenvector. Minus 1, 0, 1 is an eigenvector of A corresponding to the eigenvalue lambda equals to 2. Next, I am substituting the second eigenvector in the system 1. So if I put lambda equals to 3 in the system 1, I will get this equation matrix, right? So now I have to reduce this into upper triangular form. So for that, if you observe here, the first entry is 0, which is not comfortable for simplification. That's why I am interchanging row 1 with row 3. So row 1 and row 3 here it is interchanged. Now I have to make this entry as 0. So for that purpose, I am adding R2 with R1. So if I add R2 with R1, minus 1 plus 1 is 0. 2 minus 1 is 1. Minus 1 plus 0 is minus 1. Now I have to make this entry as 0. So for that purpose, I am adding R3 with R2. So 1 minus 1, 0. 0, 1 minus 1, 0, 0, 0. Now by back substitution, y minus z is 0, this implies y is z, and x minus y equals 0 implies x equals to y. So I am selecting y is k, therefore my x is k and z is k. So x, y, z, k taken outside, so k is not equals to 0. So I am selecting k is 1, therefore I got the second eigenvector. Similarly, if you substitute lambda equals to 6 and if you solve it, you are going to get this equation. So here I am selecting z is what? K. If I select z is k, my x is k and y is minus 2k. So k is taken outside. So 1 minus 2, 1, where k is not equals to 0 is a scalar. So if I choose this k is 1, I got this one. So now I got the 3 eigenvectors corresponding to the 3 eigenvalues. If you look at these vectors, clearly they are orthogonal. Means if you multiply these two, minus 1 into 1, minus 1, 0 into 1, 0, 1 into 1, 1. So the product is 0 here. Similarly, x2 transpose x3 is 0, x1 transpose x3 is 0. So these three vectors are orthogonal. Then I can calculate the corresponding orthonormal vectors. For that, what I have to do, I have to divide this vector with its norm. So what is its norm? Square root of minus 1 whole square plus 1 square. So which is root 2. So I am dividing this x1 with its norm, means I am dividing this vector with root 2. So then the resultant is this one. Similarly, this is norm is root 3. I am dividing this with root 3. Similarly, the norm for this is root 6. I am dividing. So I got x1, x2, x3, which are orthonormal vectors. Now the final step is, therefore, the spectral decomposition of A is lambda 1 x1 and its transpose, lambda 2 x2 and its transpose, and so on, lambda n xn and its transpose. This is the formula, but here we are restricting to 3. Therefore, here I have to write up to lambda 3 only. So lambda 1 is 2, the first vector and its transpose, 3, the second vector and its transpose, and third one and its transpose. So if I multiply this into this, I will get a 3 by 3 matrix. So this into this, another 3 by 3, this into this, another 3 by 3. So if I multiply all this, I am getting this matrix, which is nothing but our original matrix. So this is the procedure of solving the matrix A. That means not solving, it is decomposing the matrix A into spectral form. So this is the spectral decomposition of the matrix. I am Srikanth Reddy. Thanks for watching this video. I will see you in the next video.